you. Hello, and first of all, I would like to thank VELUX for giving me the opportunity of being here and present part of the work I carried out in my PhD course. And today, I'm going to show you the results of measurements that were carried out in 3 offices in Naples, in Italy. And the offices are all in the same building at the 7th floor. And we have named them Office 1, 2, and 3. It's not very original, but it works. And they all have different exposures. This is the Office 1. You can see the measured plan here. And it has a westerly exposure. And you can see also the pictures of the interior and also the external conditions. And in the graphs reported here, you can also see the spectral reflectances of the surfaces and also the furniture that are located in the room, and which were measured with the spectrophotometer. And then here you have the Office 2, which instead is easterly exposed, and you can see the same data. And this is Office 3, which is south exposed. What we have done in this research project is to measure daylight in these 3 offices during several days in each season, so during a whole year. And the measurements were carried out from morning until around 10 a.m., then after until 6 p.m. And they were repeated each hour. And we detected several data. For example, we measured the sky spectral distribution. We also measured the sky CCT. And what is particularly important in this study, the most innovative aspect that I think it is that we performed high-level measurement. As you may have heard from the presentation made yesterday, in order to take into account non-visual effects of light, it is important to evaluate the characteristics of light at user's eye level. So to do so, we placed a spectroradiometer at the same height of a person's head while seated at the desk into each one of the offices. So we placed it at an height of 1.20 meters. And then we also performed the measurements with different tilt angles of the spectroradiometer, and they are reported in the picture here. And this was done to account for the movements of a person's head, okay, which is not fixed. And so we detected with the different tilt angles, for example, eye-level illuminances and also eye-level spectral distribution, spectral irradiances. And these spectral irradiances, which were detected each hour with these different tilt angles, were averaged and used as input in this irradiance toolbox, which was developed by Lucas and other researchers. And essentially, it allows to calculate equivalent illuminances for the different photopigments in the human eye, which means that it allows to calculate the degree of simulation of the different photopigments, such as, for example, S cones, L and M cones, and also rods and IPRGCs, which are determined by a given light stimulus. So here you can see some of the results. The graphs are related to eye-level CCTs measured for each office during one day in each season. And you can see that in each one of the offices, the eye-level CCTs is never lower than 4,000 kelvins. And for example, for Office 2 and Office 1, there is a little more variation during the different seasons and during the different hours of the days. Here instead, we reported the desk illuminances. And you can see that the trends are different among the offices, which is dependent on their different exposures. And you can see that the Office 1 has the highest values during the afternoon, which is consistent with its westerly exposure. And instead, for Office 2, we have the highest values during the morning. And Office 3 instead has the highest values during central part of the day, since it is south exposed. And it also has the highest values. In some cases, we are around 4,000 lux. So in this office, there's probably a problem of glare. And also, we have the highest values during autumn and winter, because the sun is lower on the horizon, and therefore it enters deeply into the room. Here, I reported the high-level illuminances, and you can see that the trends are similar to those of desk illuminances. And there are also, in some cases, very high values. And here you can see reported the results of the application of this irradiance toolbox. And you can see these are CYANOPIC clocks, which are referred to as cones. And you can see that trends are similar to those of high-level illuminances. And the same can be said for melanopic clocks, which are referred to IPRGCs. And in this case, the values are higher than those reported before. And the same can be said for dopic clocks, which are referred instead to rods. And these are instead the graphs for chloropic clocks, which are related to M cones. And the trends remain similar, but in case for office tree, the values are a little bit lower. And the same can be said for erythropic clocks, which are referred to L cones. So in conclusion, from the presentation that you have also seen yesterday, you have understood the importance of evaluating non-visual effects of light because of their relationship with health. And to do so, there is a need also to understand, for example, the characteristics of light at user side level in indoor environments. And so there is a need to perform this kind of measurements in different environments and also in different locations around the world in order to understand that if there are similarities. And so if we can somehow develop some standard spectral distribution that could help the introduction of the evaluation of such effects in the lighting design practice. And also, another thing that is important to do is to understand how non-visual responses work, because at the present date, there is still much that is not known. So I finished. Thank you for your attention.